Hey everyone, welcome back to my number sense series. So today we're going to be talking about other sequences. Previously we've talked about arithmetic sequences and geometric sequences, which have established names and established properties, but also number sense likes to throw some other things in there to test your creative problem solving abilities, and this category of other sequences is a very real thing. And so they like to do some inventive things with these sequences, but there's not that much they can do. So often they're going to rely on one of two things, either differences or recursion. So either they're going to make a sequence where the differences between the terms have something special to them, for example, this sequence and this sequence, or they're going to rely on something called recursion, in which you get the next term from the previous two terms. So those are the two things that we're going to be kind of dealing with. And so I'll just get right into it. These are 4 different examples essentially of what I mean by these. So these should give you a pretty good idea of what number sense wants you to think about. So this first sequence is 13, 15, 19, 25, 33. So if you don't see too drastic of a change in the terms, you can try to look at the differences, because often the differences are going to give you a lot of information on the terms. So if we look at the differences here, what we're going to have is a difference of 2, a difference of 4, a difference of 6, and a difference of 8. And here it should become pretty obvious what the pattern is, right? The differences are increasing. Unlike in an arithmetic sequence where the differences would be constant, here they are increasing, and so that creates a bit of a different pattern, but it's not anything that we're going to be stuck on, because we can predict what the next difference is going to be, right? The next difference is going to be 10. And so if we wanted to find the next term in this sequence, all we'd have to do is do 33 plus 10 equals 43. Now, another note for this, in case any of you were curious, you might remember that we were able to derive a formula for both arithmetic sequences and geometric sequences. So you might wonder if it's possible to derive a formula for this kind of sequence. And the answer is yes, but it's going to be in the form of what we call a quadratic, something with, x squared in it, and it's going to be 99.999% of the time, or I might as well just say 100% of the time, not worth it. Do not try to derive a formula for these in contest, just follow the pattern, okay? Because the formulas are going to be way too overcomplicated, especially for a question like this. Not worth it in the slightest. Okay, next problem. Once again, we see the terms like 13, 5, 12, 6, 11. Once again, one of the first things we should think about is looking at the differences. So let's see what happens if we look at the differences in this one. We're going to get 5 minus 13 is negative 8, 12 minus 5 is 7, 6 minus 12 is negative 6, and 11 minus 6 is 5. So hopefully you guys should see what's going on here. We're having 8, 7, 6, 5, except every other term is negative, which is an interesting pattern, something that we're not really going to be able to find a nice formula for, but certainly an interesting pattern, and one that we can predict very easily, because it's negative 8, 7, negative 6, 5, so we can guess that the next difference is going to be negative 4. And so if the next difference is negative 4, then the next term is simply 11 plus negative 4, which is 7. Not too bad. Basically for these two, we're just going to look at the differences and see if we can spot anything. But sometimes the differences don't really tell you anything. For example, here the differences would be like negative 1, 4, 6, 60, and really there's no rhyme or reason to this. So we know that looking at the differences is going to be barking up the wrong tree here, running into a dead end. And so here is where we introduce the second kind of question that number sense likes to give you, recursion. So recursion is kind of like an arithmetic sequence or a geometric sequence. Each term is kind of derived from the previous ones. And here what I mean by recursion is kind of one of two things. Here we see that the next term in the sequence here, so okay, let's see if we can find a pattern. 3, 2, 6, 12, 72. Okay, so you might start thinking about stuff like, okay, well, it suddenly gets very big at 72 here. Where do we get 72 from? And then we might notice, wait, 72 is 6 times 12. 12 is 2 times 6. 6 is 3 times 2. So the thing we should notice here is that each term is the product of the previous two. 3 times 2 is 6, 2 times 6 is 12, 6 times 12 is 72, and so we should guess that the next term is going to be 12 times 72. And so that's what we have to do. 12 times 72. You could do this with a variety of strategies. You could FOIL it out. You could use the distributive property. You could separate this into 70 plus 2 and then, try to simplify the operations that way. You might even think about this is 12 squared times 6 if that's something you would like to do. But either way, you're going to get the answer of 864. That's one example of recursion. The next example, and the last question here, is going to be the most famous example of recursion, probably one of the most famous sequences in the world. This is called the Fibonacci sequence, named after a mathematician called Fibonacci. The sequence technically starts 0, 1, 1, and then it goes over here, but for the sake of not making the question too long, I've made it like this. So what is the Fibonacci sequence? Well, if you know it, congratulations, but if you don't, here's the pattern. Well, first of all, try to find it for yourself, of course, but if you've taken a pause and you can't find the pattern, here's what it is. Instead of having a product, we're going to have a sum. 2 plus 3 equals 5, 3 plus 5 equals 8, 5 plus 8 equals 13, so on and so on. So that's the pattern with the Fibonacci sequence. And that is basically what the Fibonacci sequence is famous for. It's also famous for something called the golden ratio, phi, but that is something you can choose to read up on later if you would like to. But the important thing is each term is the sum of the previous two. So the next term is going to be the sum of 8 and 13, which is 21. So in conclusion, with other sequences, if number sense wants to make them easily doable in your head, there's not that much they can do, right? They can't be too inventive. So basically, when you're looking at these questions, just try to keep a few things in your head. First of all, you can always look at the differences. More likely than not, there's going to be some nice pattern in the differences that you can then use. Or if that fails, you can look at recursion. So like 3 times 2 equals 6 or 2 plus 3 equals 5, things like that. Other things to watch out for, they might decide to bring in maybe like prime numbers or something, but that would be kind of rare of them. Usually it's going to be something like this. So the most important thing in other sequences, unlike the previous two, is kind of to be creative, right? You have to notice these patterns because they're not going to tell you what kinds of patterns they are doing. But if you have a few examples to go off of, it can be massively helpful. So I hope that you guys understand everything here. If it doesn't make sense, drop a comment below, of course. I will reply to it. And yeah, thank you guys for watching, and I'll see you next time.